Hey Internet student, welcome to the brief tutorial Statistics. My name is Matthias Bertel, I'm Professor for Mathematics and Statistics at the University of Applied Sciences in Offenburg, and in this video I'm going to explain three different averages, also called measures of central tendency, and the circumstances that determine which of the three averages is the right one. I hope you enjoy this video. If you do, please give it a thumbs up, but now to the measures of central tendency.
Most people are familiar with at least one way of calculating an average, which, more formally, is being referred to as the arithmetic mean. To get the arithmetic mean, we simply add up all values and divide that sum by the number of all values. In this clip, I will explain two additional means, namely the harmonic and the geometric mean. The reason is, while the arithmetic mean is good in certain situations, there are other situations in which it simply doesn't do the things that we'd expect from an average value. And that's why we need some alternative ways to calculate a mean. Of course, there's a story for means as well. It's the story of Cadwin. Cadwin owns a cap shop. He did try selling trousers, but for some reason that didn't work out. Anyways, he sells caps. In Cadwin's shop, there's a lot of caps, some cheap, some more expensive. Let's say a customer bought three caps, one at a price of $10, one at a price of $17, and one at a price of $12. The average price per cap would be 10 plus 17 plus 12 divided by 3, and that is $13 per cap. That type of calculation is, as mentioned in the introduction already, called arithmetic mean. In general terms, if we call the values for which we want to calculate an average, x1 for the first value, x2 for the second one, and so on, may xk be the last value, then the formula is sum up all values and divide by the number of values. Although there are alternatives, it is quite common to use an x with a bar on top as symbol for the arithmetic mean. I call it briefly x bar. So why is it useful to get an average like that? Given all the variety of cap prices in Cadwin's shop, an average price gives us a feel for the general situation in Cadwin's shop. Let's say the average tells us something about the center of all prices. If we also calculate that average for prices in Sibwin's shop, and let's say Sibwin sells the same caps at $8, $16, and $18, we would get an average price of $14 per cap, and we would say that it tends to be slightly more expensive in Sibwin's shop. So let's note down, we expect a mean to, in some shape or form, mark the center of a given dataset. Now, let's assume a customer purchases three caps at $10 a cap, one at $17 and one at $12. Most people now would no longer say that the average price is $13 per cap, although individual prices haven't changed. Normally one would account $10 three times simply because three caps were bought at that price. So that is 3 times 10 plus 1 times 12 plus 1 times 17. And we would divide by the number of all caps, which is 3 plus 1 plus 1, i.e. 59 divided by 5, which is $11.80 per cap. So why are we doing this? That is because we expect a logical connection between an average and the overall or total value. What I mean by that is, if we multiply the mean with the number of caps that a customer bought, we expect to get the total amount that the customer had to pay. For example, if we buy three caps at a theoretical price of $13 per cap, we will need to pay $39, which is exactly what the first customer had to pay. The second customer bought 5 caps, but if we multiply 5 caps with $13 per cap, we get $65. However, that's not what the second customer had to pay. He paid $59, and that's what we get when we multiply 5 and 1180. Let's note down that second expectation. We expect a mean to have a logical connection to the total value. Let's also note down the generic formula which the second customer used. That formula is called weighted arithmetic mean, and the values, in case of the customer, these values were prices, we call again x1, x2 up to xk. Secondly, given that it is possible for some values to occur several times, we also need so-called weights, for which I use the symbols n1, which is the number of times that the first value occurs, n2, and so on up to nk. The symbol is still x bar, and the formula is multiply each measured value with its weight, take the sum of all of that, and divide it by the sum of the weights. In the meantime, Catwin dug out 3 deliveries of a cap that will go on sale this season. Catwin needs to figure out the average purchase price per cap and applies the arithmetic mean. He simply sums up all the individual purchase prices, divides that sum by 3 and finds that the average price should be $14.33 per cap. Catwin thinks for a moment and realizes that not only the prices were different, but that he also bought 3 different volumes, one at a total cost of $240, one at $160 and one at $300. Therefore, maybe the weighted arithmetic mean might be more appropriate. Catwin calculates 12 times 240 plus 16 times 160 plus 15 times 300 divided by 240 plus 160 plus 300 equals 1420. For some reason, Catwin still feels uneasy about that result and thinks one more time. The average price must be measured in dollars per cap. The total amount of all 3 deliveries is 240 plus 160 plus 300, i.e. $700. The number of caps is actually written nowhere, but the first delivery was $240 at a price of $12 per cap. That is only possible if that delivery consists of 20 caps, which is 240 divided by 12. Similarly, the second delivery must consist of 160 divided by 16, i.e. 10 caps, and the third delivery must consist of 20 caps. Therefore, the average price must be $14 per cap. The formula that Catwin just developed is called weighted harmonic mean. To calculate the harmonic mean, we also need values and weights. The symbol is x bar h, h stands for harmonic, and the generic formula looks somewhat funny. The numerator consists of the sum of all weights. The denominator is made of the weights divided by the values for which we want to calculate an average. That is exactly what Catwin did. The values are still the prices, but this time the weights are the total costs of each delivery. The reason why things got complicated is that the weights this time refer to the numerator of the desired mean. What we're looking for is dollar per cap, which is also the unit of our individual values. But the weights that we have are not the numbers of caps, which is what we need in the denominator, but dollars. Therefore, we need to work out the number of caps first, which we could do by dividing the weights by the prices. Catwin is back to his shop and keeps selling caps. One day, a customer who bought a knit cap a few weeks ago returns and complains that the cap is completely worn out after a few times of washing. Catwin wants to know how many times the customer washed the cap so that he can file a complaint with the manufacturer. Unfortunately, the customer does not remember. Therefore, Catwin needs to find out himself. When new, the cap has a width of 6 inches. After the first washing, Catwin measures again now it is 7.2 inches. Washing the cap again, measuring 9 inches, and after the third washing the cap shrank back to 6.3 inches. So what is the average enlargement per washing? During the first washing, the material has stretched by a factor of 7.2 divided by 6, i.e. 1.2. During the second washing, the material went from 7.2 to 9, so the stretch factor is 1.25. And on the third washing, the width changed by a factor of 6.3 divided by 9, which is 0.7. Before we calculate an average stretch factor per washing, let's look again at what we expect from a mean. We wanted to represent the center of a dataset, but we also wanted to have a logical connection to the total value. The total, let's say, expansion of the cap is from 6 to 6.3 as a result of washing the cap 3 times. An average stretch factor, let's call it F for the time being, therefore would be one that, applied 3 times in a row, would also get us from 6 to 6.3 inches. Now, where is the connection to the 3 individual stretch factors, spelled out here in blue? Actually, the change from 6 to 6.3 is a result of multiplying all 3 stretch factors with the start width of 6 inches. All widths that we measured in between were not much more than interim results on our way from 6 to 6.3. Therefore, 1.2 times 1.25 times 0.7 must equal f times f times f. Now that equation is easy to solve, as f times f times f is f to the power of 3. Therefore, f, the average factor, must be the cube root of the product of the individual stretch factors. The rule that we've developed here is called geometric mean. It has the symbol x bar g. The measured values we again call x1, x2 up to xk. In Kedwin's case, the measured values were the individual stretch factors, and the rule is extract the root of degree k, k is as usual the number of measured values, from the product of all individual values. Geometric mean we use whenever we want to calculate a mean of consecutive growth factors. Kedwin's average stretch factor is approximately 1.016. In growth or shrinkage, often only growth rates are given. For Kedwin's cap, we could say that at the first washing it stretched out by 20%, during the second washing by 25%, and that it shrank by 30% after washing it for the third time. However, it is important that when we calculate geometric mean, we must not use such percentages itself, but only the change factors. A typical example in which we would use the geometric mean is the growth of capital investment. Let's suppose an investment fund grows by 20% in the first year, in the second year its value drops by 10%, in the third year its value increases by 10%, and in the fourth year the fund grows by 20%. The growth factors would therefore be 1.2, 0.9, 1.1 and 1.2. If we now want to calculate the average growth of that fund, for example to compare it with a fixed annual interest rate, the correct mean to use would be the geometric mean over the growth factors, because they form a series of consecutive changes that, taken together, constitute the overall growth of that fund. In this case, we find that the investment fund grew by approximately 9.3% per year. Both the arithmetic and the harmonic mean would give us incorrect results. Let's summarize. Kedwin has discovered 3 means. If the measured values are basically independent of each other, just as the prices of caps, we need to assess whether available weights refer to the numerator or the denominator of the desired average value. If they refer to the denominator, in Kedwin's case that was the number of caps, we need the weighted arithmetic mean. If they refer to the numerator, as was the case when we had 3 deliveries of the same cap at different prices, here the weights were the total amounts of each delivery, we need the weighted harmonic mean. If we are looking to calculate an average of consecutive growth, shrinkage, or let's just say change factors, as we did when we figured out the average expansion per washing, or when we talk about the growth of investment, for example, we need to use the geometric mean.
That was my explanation of the arithmetic, the geometric and the harmonic mean. I hope you enjoyed this video and found it useful. If you did, please give it a thumbs up and subscribe so that you don't miss any of my other videos. If you have any proposal for an additional video that you'd like me to shoot, just leave a comment in the comment section below. I thank you for watching and I hope to see you soon.